Welcome to the Explainer. We ask AI to see things all the time, right? From spotting your face in a photo to, driving a car. But here's the big question. How do we actually know if it's any good at it? It's not just a simple pass or fail. Today, we're going to pull back the curtain and really break down how we grade an AI's vision.
So let's start with a really simple task. You give an AI a photo and say, hey, find the cat. A second later, it draws a box. But is that box in the right spot? Is it the right size? Heck, is it even a cat? Answering those questions and doing it reliably is honestly one of the biggest puzzles in computer vision. And that's exactly what we're going to get into.
All right, so our first challenge is just trying to draw what's called a bounding box around our object, in this case, the cat. And as you're about to see, the things that seem super logical at first, well, they fall apart pretty quick.
So our first idea is really straightforward. We'll just chop the image up into a few big squares. Then the AI looks at each square and basically asks, is there a cat in here? If it gets a yes, we just hand back that whole square. Easy, right?
Well, not so fast. I mean, sure, the box has the cat in it, but it's also got a ton of the background. It's just not very precise. So the obvious solution seems to be, let's just use smaller patches. That should work.
Okay, let's try this again. This time, we're going to use a much finer grid, lots and lots of tiny patches. And we run the exact same play. Classify each little box and return every single one that screams cat. This has to be more accurate, doesn't it?
And nope. We've actually just created two brand new problems. First, we still don't have a clean outline of the cat. And second, now we've got a whole bunch of boxes all pointing at the same poor cat. This is just getting messy. So maybe the problem isn't the size of the boxes, but their shape.
All right, approach number 3. What if we think beyond the square? Let's throw a bunch of different rectangles at it, tall ones, wide ones, and see which shape gets the highest cat score.
We're definitely getting warmer, but we're still missing something huge: orientation. That tall, skinny box might be perfect for a person standing up, but it's totally useless for a cat that's all stretched out taking a nap. Which, of course, leads us to our final kind of brute force approach.
This brings us to what's called the anchor box method. And what this is we basically just throw the kitchen sink at the problem. We create thousands of predefined boxes, every shape, size, and aspect ratio you can dream of, and we check every single one. And look, this can work, but it is wildly inefficient. It's super slow, and we burn so much energy just classifying empty patches of sky or carpet. There has to be a smarter way to grade this.
So instead of just guessing with more and more boxes, we need a way to mathematically score the overlap of any one box. And to do that, the pros use a very specific and very cool metric.
And that metric is called intersection over union, or IOU for short. It's this really elegant score that goes from 0 to 1, and it tells us exactly how well our AI's predicted box overlaps with the actual correct answer. A score of 1 is a bullseye, a perfect match. A 0 means it missed completely.
So how do we actually calculate this thing? Well, first up, we find the intersection. That's the part where the two boxes overlap. All we have to do is find the area of just that overlapping rectangle. Next, we figure out the union. Now, this is the total amount of space taken up by both boxes put together. And the formula here is key. You add the area of the first box to the area of the second box, but then, and this is important, you have to subtract the intersection. Why? Because if you don't, you'd be counting that overlapping area twice.
And the last step is the easiest part. You just divide the area of the intersection by the area of the union, and boom, that's it. That gives us our IOU score, a single, really powerful number that lets us grade our prediction. Okay, so an IOU score is fantastic for grading one box. But a real-world model makes hundreds, maybe thousands of predictions. So how do we roll up all those individual scores into one final grade for the whole AI?
It starts by setting a threshold. We just have to decide on a minimum IOU score to count a prediction as correct. A pretty common number to use is 0.5. So if the IOU is over 0.5, we'll call it a true positive. That's a success. If it's under 0.5, it's a false positive. The AI messed up.
Let's walk through a quick example. Let's say our model made 5 different predictions for cat, and we've already calculated the IOU for each one. As you can see, we've got them ranked here from a really great score of 0.9 all the way down to a pretty bad one at 0.2.
Okay, now let's apply that 0.5 threshold we talked about.
The first 3 boxes, with scores of 0.9, 0.8, and 0.7, they're all above our cutoff, so they count as true positives. The last 2, at 0.4 and 0.2, they fall short. They get marked as false positives. It's just a simple pass-fail test.
Now we can calculate our first really important metric, precision. What precision tells us is pretty specific, but super useful. It answers the question, of all the times the model said it found a cat, what percentage of the time was it actually right? It's really a measure of its reliability.
So let's actually calculate the precision as we move down our list. After that first prediction, we have 1 true positive out of 1 total guess, so our precision is a perfect 100%. After the second one, we're 2 for 2, still 100%. Same for the third, 3 true positives out of 3 predictions, still perfect. But then we hit our first false positive at box number 4. Now our precision drops to 75%. That's 3 true positives out of 4 total guesses. And after the 5th box, it drops again, down to 60%.
So to get that final grade for the cat class, we calculate what's called average precision, or AP. We do this by taking the average of the precision value each time we find a new true positive. In our little example, that means we average the precision scores from box 1, box 2, and box 3. Since they were all 1.0, the average is, well, 1.0. This gives us one solid number that tells us how well our model did at finding cats.
And that brings us to the grand finale, mean average precision, or MAP. This is the ultimate report card for the AI. All we do is calculate that AP score for every single thing the model knows how to find. Cats, dogs, cars, people, you name it. And then we just average all of those scores together. That gives us one final number to judge the whole model's performance. So why on earth do we go through all this math? Because this isn't just some abstract exercise. These metrics, this whole system, it's the very foundation of whether we can trust our AI systems or not.
Think about it. From an AI helping a doctor find tumors in an X-ray, to the car driving itself down the highway next to you, its performance is being judged by its MAP score. That's the grade that tells engineers if a system is good enough to be let loose in the real world. So that leaves one last question, really. For these jobs where lives are on the line, what score is good enough for you?